All right, it's recording. Here we go. Fractions. We skipped 3A because that's called equivalent fractions because most students have a general idea of what equivalent fractions mean. Here, I'll show you what it means in terms of equivalent fractions. 3A talks about, say, this pizza here. It originally was a whole pizza. And then someone's eaten one huge piece out of the two pieces that are available. So we say that's half. So half a pizza's gone, right? Now on this side, this is also another pizza, whole pizza. And again, I've cut it into fours now. So cut it into four pieces. So one vertical, one horizontal. There are four equal pieces. And in this case, I eat two of them. So two out of the four pieces have been covered. But why are they equal? Because you have still half a pizza left. The only difference between the two is how many cuts you made. So here you got two pieces, but that's a lot bigger piece. Here you got four pieces, but it's a lot smaller than the first one. Then you go to the third one. I'm now cutting into six. So what I did was I cut down, cut diagonally, and then diagonally. Now I get 1, 2, 3, and then 1, 2, 3. That's six pieces in total. And here if I eat 1, 2, 3 again, 3 out of the 6 is still half. So the only difference between them is that the numbers that you see, the number of pieces you cut, changes the number of pieces you eat. But overall, the total quantity is the same. Now, how do you figure out whether they are actually equivalent or not? It's based on the denominator. So the denominator talks about number of pieces. That tells you how many pieces you cut up. So when you say, how do you know that 1/2 is the same thing as 2/4? The first thing you need to ask is, what's the multiple of 2 and 4? Okay, or what's the factor? Now we can see that if I double 2, I get 4. But if you double the denominator, you're going to double the numerator, keep it balanced, right? It's like if you had $5 and I doubled one side, then I make sure that I double the other side, otherwise it won't equal. If you didn't understand what I just said there, here's an example. You know, if you have $5 and a $5 note, how much does that equal? $10 note. Now here's the thing that some students don't realize in terms of mathematics. So you got two notes on that side, this side you have one note. That's different, yeah? Two notes versus one note. But the logic is this. When we teach mathematics, we say times 2. So if I double this side, how much should this person have now? $20, right? But here's the mistake that a lot of students do when they do maths, but they don't understand why we do that, okay? This is what they do. They say if you times it on the right, you also have to times on the left. This is what they do. They do times 2 on the left, so times right, times left, nothing wrong. 5 times 2 is 10 plus the 5, and suddenly there's an error. What's the error?
They didn't include the other 5, which is part of the question.
Yeah. See, when I do it in terms of notes, kids get it. But when I do it in algebra, which is what you might have done last year, when we do like A, B plus C, they say expand the brackets by multiplying A times B and then A times C. A lot of students only ever do A times B and they forget the C. But funny enough, when I do the money component, they're like, oh, that makes so much logical sense. But they just don't see it. How is algebra linked to money? It's the same thing. Because if you only double this side, just the $5, you're missing out on $5 here because they came together. Together is $10. You had two sheets. So if you double one of the sheets, you have to double the other sheet. Otherwise, it doesn't make sense. But most students don't see it until you actually give them something concrete to think about. So that's why when it comes to mathematics over here, it's the same thing. When I say double the bottom, why do you also have to double the top? Because it comes together. It's 1 for every 2. So if you double the bottom, you have to double the top. Otherwise, it doesn't make sense. But a lot of students forget that step. They just do times 2 and they're like, yep, all good. And they'll write their answer as 1/4. And they're like, oh, I just forgot that step. But that tells me you never understood why we do that. You just memorized a process that has been taught to you since primary school. So I want you to understand into the $5 notes, you had two $5 notes. You doubled the right-hand side, which is 10, makes 20. That's true. But when you double the left, because you have two of them, got to make sure you double everything. This one has two parts. It has a numerator and denominator. So when you double one part, you have to double the other part. Otherwise, it won't make sense. Okay? Same thing with the third one. So again, we look at the denominator and we say, well, this was 2. That's a half. That's the simplest form you can get. So from the simplest form, you should be able to get to 6. How do I go from 2 to 6?
Times it by 3.
Times it by 3. But whatever you do to the bottom,
Do the top.
do it to the top. So you times this by 3, and that's how you get 3, 6. That's how you keep it equivalent. Okay? If the numbers don't match, if you times this by 3 and you times the top by 3, but if it's not 3, 6, it's not equivalent. That's exercise 3A. So those who struggle with equivalent fractions on what I'm trying to say now, then it's worthwhile looking at 3A again as a revision of last year in primary school. Okay? Because it really ties in the logic as equivalence. Beyond equivalence now I'm going to tell you the next bit. What I want you to realize is each of these pieces, now I'm going to change them. So I'm just going to delete all this. It's taking a while. All right. There's one fact that you all can see without me telling you. You can see that this piece is one piece. You can see that this is also one piece. You can also see that this is one piece. This is 1 out of the 2. This is 1 out of the 4 pieces. This is 1 out of the 6 pieces. Are they the same pieces? No. Logically, no. Yeah, because if I asked you right now, which piece of the pizza do you want? If I actually had a pizza in front of you, most of you would likely choose this one, even though it's one piece. If I said you can get one piece, go choose one, you wouldn't choose this one because you get a smaller portion of it unless you're, calorie restricting. Most people choose this one because you get bang for buck. One piece, and I didn't tell you which one, you would choose this one because it's bigger. So what I'm saying down here is when you write a fraction 1 out of 2, 1 out of 4, 1 out of 6, 1 out of 8, they're not the same. They are inherently just as different as you sitting next to the person next to you. You guys are different. Just like the chairs, my chair, that cushiony chair there, is not the same as your plastic chair. They're both chairs, but they're not the same. They're both fractions, but they're not the same. One is bigger than the other. Okay? This is one of the core key concepts as to why, when you learned how to add and subtract fractions, why we had to do what we needed to do. So I'm going to show you an example. Each piece of the pizza is, and I want you to write this in, this is a really key concept. If you get it, you understand why we do the way things we do. So, they are different. Now I want you to see this example down here so you can understand what I'm trying to describe. You see, if you picture the actual what the fractions mean, this means I've got 2 pieces of the pizza. I've got 2 pieces of the pizza. I've got 2 pieces of the pizza. They're all cut in 2s, right? So it's cut into 2. 1, 2. 1, 2, 1, 2. What this is saying is I've got 1 of them. And then you add on, I've got 4 of those halves. That's what this means. This means 4 of what type? What type of fraction do you have? I've got halves. So what I'm adding on is I've got 1, 2, 3, 4. So here we go. This is 4. 1, 2, 3, 4. And then the third one, I've got halves again, but this time I've got 3. This is why when you add the fractions back in primary school, they always said check. What do you have to check before you add fractions? The denominator. You have to check if they are the same. Why did they ask you to do that? It's because you're guaranteeing the pizza is the same size. If they're the same size, now you can count them. You got 1 of those halves, plus 4 of those halves, plus 3 of those halves. So together, how many do I actually have? I got 1 plus 4 plus 3, which is equal to 8. 8 halves. That's what that means. This is the reasoning as to why you needed to make sure the denominator is the same, because you're talking about the same type of pizza. It's like the chairs. If I asked you right now, how many of those red cushion chairs do we have in this room? How many do you say?
1.
There's 1. But it would be ridiculous if you said it's 1 plus, there's 24 of you here today, plus that extra one there, plus that extra one. So that's 26 seats. It'd be weird if you said 26 grey chairs plus 1 is 27 chairs, because they're not the same. You can't add them. That's why you couldn't do this back then. In primary school, when they were teaching you half plus a third, what a lot of students do is they do 1 plus 1 is 2, 2 plus 3 is 6. But right off the bat, that doesn't make sense, because you're talking about half of a pizza, which looks like this.
Wait, but Mr. Tran,
Yeah.
2 plus 3 is 6. It's 5.
Oh, sorry. Thank you. I was testing you. 2 plus 3 is 5. So right off the bat, you're already wrong, because this means the pizza that you have, it's this size. The 1/3 means that your pieces look probably more like that. They're different. Because they're different, you can't count them. Just like the chairs, if it's red and grey, you don't count them the same. One's a red chair, one's a grey chair. So you count the number of greys or you count the number of reds. But they're not the same. That's why we can't count them. You can't add these two. It's impossible. So what did they do? What was the technique in order to do this? Since there are different types of pizzas, then we said, how about we change these fractions to something that is the same? Just like how we did up here, a half is the same thing as 2/4. 2/4 is the same thing as 3/6. 3/6 is the same thing as 4/8. We can change the denominator. Because of that, this is what you have to do. 2 and 3s. Where do they have a common multiple? So let's think about it. 2s, if I double it, I get 4. If I triple it, I get 6. If I quadruple it, I get 8, and you follow on. That's your 2's times tables. Then you look at 3s. Start off with 3. If I double 3, I get 6. If I triple 3, I get 9. And then I get 12, 15, 18. This is your times tables for 3s. Now, where do they both have in common? The 6's. So that's why you then said, based on equivalent fractions, you said, well, half, I had to times the 2, I had to triple it to get to 6. So I triple the bottom to get to 6, and I triple the top. Whatever you do to the bottom, you got to do to the top. That's how you change this fraction into 3/6 plus. How do you change 3's to 6's? You double them. It takes double the amount, and that's why you get 6 and 2. Now you can count them. See, this here, if you read the fraction as it is on a conceptual point, do you see what this actually means now? This is saying I've got 6's, which looks like this. And I've got 3 of them, plus another 2 of the same pieces. You can count them all together. That's why we know the answer is 3 plus an extra 2 of those 6's is 5/6. So at the very core, if you didn't sort of understand the technique back then, the reason why we had to change denominators is because you're talking about very different quantities. Just like the chairs, they're not the same. Not all tables are the same, and not all people in this room are the same. You're all people, but you're individually different. So unless you can clone yourself, then how many of, like James there are, you count the number of James. How many Mr. Trans are there? You would count the number of Mr. Trans. But right now, we're all different, just like fractions. Fractions are each one that you write in the denominator is a different one. Your goal is to learn to make them the same. Does that make sense? Okay, so that's the core. If you didn't get that, it's okay. I'll teach you the technique and you can just get by. But I didn't want you to memorize. Why do you just always make sure the denominator is the same and that you have to make them the same before you add them? That's what students tend to make mistakes with, because they're memorizing and not understanding. Yeah? All right, let's do this example just so you get a feel of it. Here we go. So we can see 1/2 plus 5/6. First thing is, are they the same type of fraction? No, this is a half, a lot bigger. You're cutting a pizza into 2 pieces versus 6. If you cut it into 6, it's a lot smaller. So they're 2 different pieces already. So now you need to make sure they're the same. So go through your 2 times tables. Your 2 times tables, you can double it, you can triple it, you can quadruple it. So that becomes what? 2 out of 4, 3 out of 6, 4 out of 8. There's probably a lot more. Versus the 6's. If I keep them in terms of 6's, if I double it, I get 12. If I triple it, I get 18. If I quadruple it, I get 24. So that means it becomes 2, 3, 4. Okay, so that skill there, that skill is exercise 3A. So if you need to revise that, that's what you do in 3A. Now, where do they both share the same type of fraction? 6. No. That's the lowest common multiple. Okay, so lowest common multiple of 2 and 6, they both have a 6. So because of that, I can rewrite the equation instead of saying half plus 5, 6. They're two totally different ones. They're not the same. Because they're different, I will now then say, well, let's convert the half into 3, 6. The 5, 6, since they're both already 6s, that's great. They're the same type of fraction. So in your notes here, this is what I want you to write. LCM is 6. We need 1/6 type fraction. We've got them. So here we go. 1/2 to 5, 6 is the same thing as writing 3, 6 plus 5, 6. So together, how many 6s do I have?
8.
8. So you do 3 plus 5. Notice my layout. I want you to copy my layout. See how I'm laying it out? So I went from, this is the question. I changed the denominators, equivalent fractions, to make sure the denominators are the same. So they're the same type of fractions. Then what did I do in the next line is I'm showing you what I did. I added the numerator. The reason why I put this line is because a lot of students skip this step and they just do the answer. But then when they revise, they forget how they got there. And they might do 6 plus 6 in the test. Very common. I see it in the test all the time. They do 6 plus 6 or 6 times 6. But it's just losing that understanding. So that's why that mediocre step is important. Okay? So the intermediate step, make sure to write this one in. So that reminds you it's 3 plus 5 because that's how many of those 6s you have. Together you get 8, 6. Now, for those that are stronger students, you don't leave your answer as 8, 6. Why?
Because the numerators are the denominator.
Yeah. Okay, no, you can and some degree, but for most answers, especially at year 12, they want in simplest form. So simplest form is either you simplify that number a lot smaller first, and then you convert if it's an improper fraction, because this one's bigger, so the top number is bigger than the bottom. Bottom is denominator. So if the numerator is bigger than the denominator, you should be writing it in mixed fraction form. Anyone know? Let's simplify it first because 8 over 6 can be more simplified. 8 over 6 is the same thing as, Fraser?
1 to
I want something a bit smaller. See how it's got 2 over 6? I didn't want that. So I want you to simplify this fraction first. 8 over 6 can be smaller.
4 over 3.
4 over 3. Because you then look at what number goes in 8 and 6 to get there. So you got to think about factors. And we can see 2 can go into 8 4 times and 2 can go into 6 3 times. Simplify this first, then convert it into mix. Otherwise, you'll get this answer here, which is not simplest form. See, now 4/3, what is that as a mixed fraction?
1 and then 1 over 3.
Very good. So how many 3s fit in 4? Fits in once, one whole, with a remainder of 1. That's why the 1 goes up here. And we're talking about thirds right now. So this is the type of fraction. So it's one whole and one of those thirds left over. That's what the language is saying. It's talking about the type of pizza you have. Yeah, so you got 1/3 of a pizza. That's thirds. You got 4 of those thirds. That makes one whole and 1/3 left over. That's what it means. Yeah? Better than leaving it as 8, 6. And if you convert it to mix, you see you can still make 2, 6 smaller. 2, 6 is technically 1/3. And that's what I mean. If you simplify it early, then you don't have to do that step extra. Then you can just move to the correct answer. Cool? All right. Can I get a show of hands just out of confidence? Did you understand? Hands up if you understood what I meant by making the denominators the same. Hands up if you understood the reference to the pizza. Okay, good. Because that's key. That's core as to why you add and subtract that way. Yeah? All right, here we go. Flip over the page. All right. Converting mixed fractions to improper fractions. So what we can see here is when you convert 3 out of 2, we know this means See, the denominator is 2. So it means the pizza has been cut into 2 pieces. That's what the 2 means. I've got 3 of them. So here's one of those halves. Here's another one of those halves. Here's another one of those halves. So that's a half plus a half plus a half. That's what this means. Half plus a half plus a half is the same thing as 3 halves because I've got 3 of them. Yeah? So what you realize is that these 2 together, 1 out of 2 and 1 out of 2 will make one nice whole pizza. So you get one whole pizza. You get 2 halves make one whole. And you still have that remainder left over, which is 1 over half. So here we say 1 whole pizza and half of a pizza left over. How do we do it mathematically? Well, since you know it's out of 2s, when you say 3 out of 2, this actually just means 3, and the symbol means divide. So share it for 2 pieces. How many 2s fit into 3? So 3 divided by 2. Now you can do that on a calculator, or you can do short division or long division. How many 2s fit into 3? Now I wrote it as a decimal so we can work into the remainders and all that. But here we go. 2. How many 2s fit into 3? 1 whole. Remainder? 1. Now if we were to carry it, you normally carry the 1 and put the 1 on the 0 here, and that becomes 1 whole is 10 tenths. That's what it means. Yeah? But instead of doing that, what we do now is we say 1 whole, remainder is 1. So this is how you write it. It says 1 whole, remainder 1. And what type of fraction were we working with? Halves. So that's why we say 1.5. Okay, so 1/2. That's how you convert improper fractions. You literally do what it says, 3 divide 2. You can work it out in decimals, or you can work it out as how many wholes and what's the remainder. Okay, so I'm going to write here, wholes, remainder. And this is the type. That's the key, the biggest thing that I'm trying to teach you to understand. Each denominator is a type of fraction. And if you think of it in terms of pizzas, you can understand the larger the number, the smaller the piece. Yeah, so if I said 300s, you're essentially getting a pizza and you're cutting it into 100 pieces and you get 3 of them. That's how small it is. Yeah, so the larger the denominator, the smaller the actual piece is. That's a very powerful thing that I still teach my Year 12s, where I talk about what if the number gets infinitely large? What happens? And they still struggle to imagine if I made this infinitely large. So if I made this 1 million, what happens to the number? Gets smaller, infinitely smaller, almost close to 0. Because you're taking something like $3 and you're dividing it by 1 million people. Each person's got to get like a millionth of $3. It's very small. Okay, so that's the concept at Year 12 that I still have to remind them. The larger the denominator, the smaller the value. Yeah? All right, here we go. So that's improper into mixed fraction, or mixed fraction to improper. And we'll stop at this example, and then I'll let you guys practice the adding and subtracting. Okay? Sorry? Yeah, for 3B. Now, just a reminder, does everyone here, can I get a show of hands if you remember how to convert mixed fraction into improper fraction? Hands up if you remember how to do it. Okay, that's about half of you. Okay, I'm going to make sure that you know how to do it. Here we go. This is how you convert 3 1/5. 3 1/5. Show you the short method first, and then I'll show you the logic. Okay, so the short method is, if you got 3 1/5, remind me again, what do? How do you convert it? What's the short way?
3 times 5.
Good. Take the denominator times by 3, so times by the whole number, and then add the 1. That's the quick way to do it. Okay, so take the denominator, multiply by the wholes, then add to the numerator. Okay, write that in. So multiply denominator times the whole, and then add to numerator. That's the method. That's the short method. A lot of students will memorize this. The question is, why does it work? Here's why it works. 3 1/5, 3 wholes. Now, what type of fraction am I working with? Mixed, yes, but in terms of the denominator, what type of fraction is it? It's 1/5. Okay, so the type of fraction is fifths, right? So that means you're going to convert the 3 wholes into fifths. Now, 3 wholes is 3 out of 1. That's what 3 wholes mean. So how many wholes? That's 1 whole. 3 of them means 3 out of 1. Now, you need to convert it to fifths. So in order to change 1 to 5, see how you have to times it by 5 already? That's why all the whole numbers, no matter what the whole number is, you're always going to times it by whatever the number is in the denominator. That's why you times this by 5, but whatever you do to the bottom, you times to the top. This is why, once you have the same type of fraction, why do you add the numerator? Because they're the same type of fraction. You got 15 of these fifths, plus 1 of these fifths. 15 plus 1, that's how you end up with 16 fifths. That's why you do that. So this is the logic as to why the formula works. But that's the formula. Denominator times the whole. Why do you do that? It's because every whole number is out of 1. And if it's always out of 1, you're always going to times by whatever the denominator is to make them the same. So if this was 6, it'll be 1 times 6. If this is 7, this would be 1 times 7. But if you do 1 times 7, you're going to times the top by 7 as well. That's why it works. Same thing with this one. If you have a look at this one, 2 3/4. What type of fraction is this one? Quarters. This is quarters. I've got 2 plus 3/4. But that's 2 wholes. 2 wholes is the same thing as saying 2 out of these 1 wholes. That's 1 whole. But to change that 1 to a 4, I have to times this by 4. That's why it works. That's why it ends up being 8 over 4 plus 3 over 4, which gives you the answer of 11 out of 4. Okay? That's why the technique works. So if you look at the technique, 2 3/4, why do you always do 4 times 2? It's because of this. They're skipping this step. Instead of teaching that to you, instead of saying 2 wholes is the same thing as 2 out of 1, and then that's a 4, so you have to change this to a 4, you times this by 4. Instead of doing that, instead of teaching you this step, this is all they tell you. That's why students know how to do the fractions, but they don't know why. They just do it. They just do it because I tell them to. But you do 4 times 2 only because you end up doing that anyway. Times this by 4, so you have to times the top by 4. That's where it comes from. And then why do you add the numerator? Because now they're the same denominators. 8 plus 3 gives you 11. That's why it works. Okay? So again, if you didn't understand the theory, you can memorize. But I don't like memorizing. To me, it's if you understand the core, you get the logic much better. Yep.
So if the one on the right had the different denominator, would you have to do the timing only for that one as well?
This one?
As I'm saying, if it was different, the denominator would, if that one was 4 and that one was 1, would you have to do the same thing?
If this was 8.
No, that was 1 and that was 2.
If this one was 4 and that was 1.
Yeah.
So you,
The same thing.
well, if this was 4 and that was 1, then you would have had something like that. Is that what you're saying?
Yeah.
Yeah, well in that case, same thing. 2 quarters, so that's a 4. But 3 as a fraction, 3 wholes is the same thing as saying 3 over 1. So you have to do the same thing. How do you change the 1 to a 4?
Yeah.
Times it by 4, times the top by 4. So you get 12. And then now they're the same type of fraction. 2 plus 12, you got 14 of these quarters. Yeah. So if you swap the numbers, if the numbers were different, that's what you would do. Yeah. Very good. All right, team, I'm going to stop there because there was quite a lengthy video, but I hope you had a better understanding of fractions and what it meant. I'm going to stop the video there.